Well, hello there. How are you doing? For those who don't know me, I'm engineer Leonardo, graduate student in fluid mechanics. Um, on this video, it will be the continuation of videos and lectures series on fluid mechanics concerning especially the Navier-Stokes equation. In which we do some considerations, demystify many concepts regarding this famous equation, which is very known but not sufficiently understood by the people who use it every day in numerical simulations, CFD, and so on. Well, in the previous video, we talked about each term in the Navier-Stokes equation. We deduce some of its terms. How do we get from Newton's second law of motion to this equation in particular? We've shown that this term on the left side of the equation is the acceleration term, okay, and this is the summation of forces per volume of fluid, right? In this case, volumetric forces. So here is the temporal acceleration, the convective acceleration, the pressure acting on this fluid, and here on the right side, the right hand side, is the viscosity, the force due to viscosity, which is known also as the diffusive term. Okay, so here is the temporal acceleration, the convective term, the pressure, and the viscosity, and also diffusion of velocity. So this equation is written in a very compact form. There are other forms to write it in a compact way available. Okay, so in this video I will talk about many forms available to rewrite and to express the Navier-Stokes, in which we will see along scientific papers along the internet, in journals of scientific journals, in books of fluid mechanics, and even in manuals of software like OpenFOAM, ANSYS, non-commercial and commercial software, free source and non-free source softwares. Okay. So first of all, one of the first forms I would like to talk about in this video is the form that is mostly known by engineers, which is where we separate each of the velocity components in U, V, and W. Okay, so these are the unit vectors U, I, J, and K, and each of the velocity components are expressed as U, J, and K, right? So this equation actually is of course a vector differential equation, where we can express as three individual scalar equations for U, V, and W. Okay, so this is equal to these four equations right here. Also, I expanded the Laplacian term, okay, which is given by the nabla operator squared, and the gradient of U. Well, if you take the gradient of a scalar variable, you obtain a vector field. But if you take the gradient of a vector field, you obtain a tensor. So here it is our members of the tensor, right? And here is our vector v, the velocity. Okay, in this case v is used as u, but you can express as u and v, doesn't matter. Okay, and also here is the gradient of p, which is the pressure. And pressure, as you know, as I discussed in the previous video, pressure is a scalar variable. So when you take the gradient of a scalar variable, you obtain a vector field, which is expressed here. The three components of the gradient of pressure, which is pressure itself is a scalar field. So here is the, let's take for example the x component of the Navier-Stokes equation, which is also a conservation of momentum equation, which is also corresponds to Newton's second law of motion. So here we have our temporal term of acceleration. Here it is the convective acceleration, where we have three components of the u vector velocity vector multiplied by this tensor. Okay, here it is the force in x direction due to the pressure, and here it is the viscosity stress. In this case, the shear stress acting on x direction. The other direction as well is straightforward. It's the same reasoning, the same mathematical deduction as the x direction. But as you can see, when you write these three equations, these three sets of equations in a piece of paper, you note that these are quite extensive, highly extends to write, right? So this is not convenient at all. There must be a more compact way to express these three equations besides that. Okay, if you're aiming to expand this equation in the three equations for each direction, x, y, and z. Of course, along this video we'll talk about the Cartesian coordinates, but in another video I'll talk about other systems of coordinates such as cylindrical coordinates, spherical coordinates, and so on, which are the most used systems of coordinates. Of course, the Navier-Stokes in this form is independent of the system of coordinates. Here it is only valid for Cartesian coordinates, so keep that in mind, right? So this form here is actually just the same as this form, but is written in a more compact way. Mathematicians like this form very much. You often see in books of fluid mechanics written by mathematicians this form, in which take, for example, the derivative, the partial derivative of u in respect to t. Here you have the partial u divided by partial t. Mathematicians prefer to write this as u subindex t, okay, which is much more convenient, is very much more straightforward to write, and it of course gains a lot of space if you study these equations in a piece of paper. So these are very convenient forms, but if you're studying Navier-Stokes in a more general way, you would prefer to not work with the expanded forms of the equation, which are these two. Okay. If you're looking then and then for a more general perspective, you don't have to open them in the three components. This only has to be achieved when you're solving them numerically or in analytically form. Okay, there you have to expand the Navier-Stokes in the three components. So, uh, returning to the compact form of Navier-Stokes, which is this one. In more advanced books of fluid mechanics, and that includes books that deals with turbulence modeling, large eddy simulation, and runs Reynolds average Navier-Stokes simulations, turbulence modeling in general, and as well scientific papers and etc. You will see that this form here is often presented in a form that includes indexes, which is, I'll move some advance a little, is this form here of Navier-Stokes, which you can see is U subindex I, U subindex I, X subindex J, and so on. This form here, also known as Tensor Form of Navier-Stokes, or Navier-Stokes using Einstein's notation, you will often see in this kind of works, including books, papers, and so on, even manuals of certain software. So for those who never seen something like this, a typical undergraduate engineer student, even initial graduate student of physics, of engineering and mathematics, find it pretty difficult to understand this kind of equation. It is not very straightforward. It is not very properly introduced in the a typical course of advanced fluid mechanics, as well as turbulence modeling, the study of theoretical turbulence, and so on. So many doubts arise with this equation, this form of Navier-Stokes equation in particular. Myself, I find it pretty difficult to understand this equation when I first saw it. So I've done some tricks to make it more easy for me to understand this notation, which I will talk about now. So first of all, I'll introduce the Einstein notation, or the sum convection for repeated indexes. Sorry. Right? So, what exactly is the Einstein notation, or the sum convection convention for repeated indexes? Well, if you have something like this, which is u, a certain variable, in our case the velocity, subindex I multiplying u subindex I, it is equal to the sum of ui, in this case from I equals 1 to 3. Okay, so this is equal to this. It is a compact way in order to avoid the sum. And it's equal to 3 because here we are dealing with three-dimensional Navier-Stokes. So we have the three components of velocity. In case you're studying a two-dimensional phenomena, it will be from I to 1, I equals 1 to 2, okay? So when we expand this sum, we obtain u1, u subindex 1, subindex 1, plus u2 plus u3. In our case, u subindex 1 is equal to u, the x component of velocity, and u equals 2, u2 is equal to v, and u3 is equal to w. So this is actually equal to this u squared plus v squared plus w squared, right? So if you understand this, you understand the principle behind this notation here to express Navier-Stokes. Okay. So moving forward, with this convention, with this mathematical tool, we can express many operators of vector calculus, tensor calculus, in a compact form, in a more elegant and straightforward form to express differential equations, particularly partial differential equations and some very complicated equations. Okay. For example, the continuity equation, as you know, is the divergent of u equals 0, right? Is this equation here, which is nabla operator, which is given by the partial derivatives of a certain function multiplied by the respective unit vectors, right? The base operators for the Cartesian coordinates x, y, and z. So we can express this as this expression. As you can see, there is I and I index here, repeated twice. So that indicates that we have to sum from I to equals 1 to 3 along this dimension. So this is actually one equation. It's equal to this, right? So this is equal to sum from I equals 1 to 3 along ui equals 1, u2, u3, and x respectively to u from 1 to 3. Right, so we obtain this equation, which is actually the continuity equation, the divergence of a certain vector field, right? The gradient of a scalar field. For example, the pressure term in Navier-Stokes equation. How can we express it using the Einstein's notation for differential equations? So here we take partial p, partial x, y. So here, as you can see, there is no repetition of the index I. However, that indicates us that these are actually three equations expressed as one equation, because I goes from 1 to 3. So when you write the gradient of a scalar field in this form, remember, when you take the gradient of a scalar field, you obtain a vector field. So here you must have three equations, which are the three components of a vector. So when you write this, you have three equations. Remember, you have to go to I equals 1, so I equals 3. So there you have, for example, for the fundamental equation of hydrostatics, you have this in the most known vector form. But if you write it using Einstein's notation, you obtain this, okay? So Gi are the components of the gravity vector, the acceleration of gravity vector in all the three Cartesian coordinates, orthogonal coordinates, okay? So this equation here, when you take u equals 0 in a Navier-Stokes equation and you consider the gravity, the volumetric force due to gravity, you obtain this equation here. So these are actually three equations in the x, y, and z direction, or in the 1, 2, 3 base form vectors in the vector field for Cartesian coordinates. So here they are, these three equations. Of course, you can substitute x subindex 1 for x, x2 for y, and x3 for z. Okay, and g1 to gx, g2 to gy, and g3 to gz. I think you've got the point at this. You've got the reasoning behind this notation at this point. Okay. So moving forward, how we can express the Laplacian operator in the using Einstein's notation. Okay. Remember, take for example the x direction of a Laplacian of u. Okay. So you have a sum over the three directions x, y, and z. So you must have some index repeated. But remember, u is a vector. U is composed by three components: u, v, and w. So we have, in this case, we will have to deal with two different components for our Einstein's notation. That's why we use the j index here. You notice ui is not repeated, which means, according to our previous mathematical deductions, we will have three equations for each u component, from u1 to u3. Okay. But as we have xj repeated, for a particular ui, we have to repeat this sum for each direction. So this also, by the same logic of reasoning of the previous equation, in this case the gradient of a scalar function, this is also composed by three equations separately. Okay, and it's important to note that this is not the same as this. Why? Well, you can see here that there are no repeated indexes. It's I and j. So in this case, you would have not only three equations, but you have 3 times 3 equations, which gives us 9 equations. And if you had this ui xi, it would be equal to this. You see that we have repeated indexes, so we have to sum over this dimension, this particular dimension. So we'll have something like this. So a good exercise is to go from this to this, to demonstrate how do we get from Einstein's notation when we expand it as a sum to using the nabla operator. Remember, x1 corresponds to x, x2 corresponds to y, and x3 corresponds to z. Okay? So this is not equal to this. Keep that in mind. When you have a sum of a certain dimension along a certain, for a certain index, you have to express it like this. That's why we don't express this as this, or x subindex j. Okay? So keep that in mind. It's very important. Well, so applying this mathematical tool, we can arrive at Navier-Stokes at this form. Okay, but for some people it can still be very confusing to think of Navier-Stokes as this. Okay, it's not when even when I study this convention, the Einstein convention regarding the sum for repeated indexes, it was still not very straightforward to me. So I developed some other techniques to make it more visually understandable for my engineer vision of the world. I believe for some mathematicians it can be more straightforward, and even for some physicists. But for engineers, this is a rough, sometimes a very rough way to look at Navier-Stokes. Okay. Well, so before I talk about a more straightforward to visualize the Einstein notation, I'll do some algebra, and well, we'll divide this equation by ρ, which is the density of the fluid, and we obtain in Navier-Stokes in this form, which is often seen in academic books. Well, as you can see here, the gradient of P, pressure, gets divided by ρ. And here, when you divide the dynamic viscosity for P, you obtain this new variable, new constant here, which is in this case is nu. Okay, this is known as the kinematic viscosity. So when you're studying turbulence and you're simulating numerically some fluid flow, it is much more straightforward to think of the importance of the magnitude of this term here by the kinematic viscosity. So the kinematic viscosity is nothing less, nothing more than the dynamic viscosity divided by its density. Okay? So be careful when you look at some tables regarding your fluid, or which can be water, air, and any Newtonian fluid which has constant viscosity, constant dynamic viscosity. You have to keep in mind if you're looking for the kinematic viscosity or the dynamic viscosity. In this case, you only have to go from one to another. You have to know the density of the fluid. Okay, so keep that in mind. Well, this form here of Navier-Stokes is often is seen quite often in many textbooks. So from now on, I use this form of Navier-Stokes. Okay. Well, returning to our main subject here, which is the Einstein's notation of Navier-Stokes. How can we see this in a way that's more understandable for one which is not very familiar with the tensor notation or Einstein's sum notation? Well, there is some mathematical trick we can use to make this more understandable. Well, the main concern of someone who is studying this form for the first time is how do we go from here to this, from the Einstein's form to the vector form. Well, what you can do is think of I as a row index for a matrix and J as a column index. So when we do that, we expand this equation in the three sets of equations. But here we'll put in a matrix form. So we have one equation expressed in a matrix form, which of course have at least three rows. So this term here, if you remember, I corresponds to the raw index. So we have here our vector of the temporal acceleration. Here we have the vector u, which is the velocity, expressed here in matrix form. Remember that you can express a vector in matrix form. It can be a matrix of one column, or you can express it as a matrix of one row. It depends on the convention utilized. But here we have a tensor, so it has to be a matrix of three-dimensional, a three column and three row matrix. So there you go. It is a tensor, right? So it is a scalar product of the u vector and this tensor here. This term corresponds to this term, right? And well, for the gradient of a scalar, as I said many times before, when you take the gradient of a scalar field, you obtain a vector field, in which case it's here the gradient of the pressure term, which is, of course, a vector, right? And here it's also a vector, which is each of its components, x, y, and z components, corresponds to the three components of the viscosity force acting on the fluid, right? So if you write each of these equations for I and use the sum convention here, remember here you have j and j, so I have to sum over j and repeat it for I to 1 to 3. You can arrive at this form on Navier-Stokes, which I believe you will not see in any textbook. This is very uncommon form of Navier-Stokes, and it's not very useful and straightforward to write in a piece of paper or in a mathematical deduction. But I believe this form of Navier-Stokes can make it more understandable, can make the Einstein notation more understandable for beginner students of advanced fluid mechanics. Okay, and besides that, there are even more compact forms and some more elegant forms, some believe, to write this form of the Navier-Stokes using the Einstein notation, which will be the topic of the last part of this video. Okay, so to do that, we define the rate of strain tensor, which looks like this. Okay, so we have the partial derivative of ui xj uj xy. So the sij component of this tensor, remember you have to go, I stands for the raw index and j stands for the column index, so we have to go to I to 1 to 3 and j to 1 to 3. So this is a tensor, right? This just called the rates of strain. And concerning the stress tensor in the Navier-Stokes equation, which is this term here, is the gradient of the stress tensor. Sorry, it's the divergence of the stress tensor, because we have to go one dimensional below the dimension of the tensor. We can write the stress, the total stress acting on a fluid, or the total force per volume acting on a fluid, as the pressure force plus a shear stress. Okay, on this shear stress, we will use our constitutive relation, which is the Newton's second law of viscosity, which can be written as this form. So tau subindex ij is equal to 2 times the dynamic viscosity times the rate of strain tensor. Okay, so using this we can write this total stress tensor on a fluid as P plus the viscosity stress according to Newton's law of viscosity. Okay, so here it is the Navier-Stokes equation, here is the divergence of the stress tensor, and now we can write Navier-Stokes in an even more compact form, which looks like this. This equation is much more generic and powerful than this one, because it made no assumptions regarding the constitutive law of viscosity. So this equation here is valid for Newtonian fluids and non-Newtonian fluids. Of course, for non-Newtonian fluids, you have to make some assumptions for the shear stress tensor of the fluid. You have, in either cases, Newtonian or non-Newtonian fluid, you have to obtain some constitutive relation for the shear stress. So here it is now no longer the Navier-Stokes in its classical form, which is for a Newtonian fluid, but we have a more general form of the conservation of momentum equation, which one of its particular cases is the Navier-Stokes equation. Well, don't forget to subscribe, to comment, leave some criticism on this video and what you hope for the next videos to come. Well, see you guys next time. Hope you enjoy.